Welcome again. Thank you for continuous support to our channel. We will discuss, in this lesson, what is power factor correction? Why is it required? How is it achieved? I had created this program software for much better presentation, and can easily understand this lesson. You can see on the screen, the electrical circuit diagram. A lighting lamp is a pure resistive load, in series connection with the equipment pump, as pure inductive load. A power factor correction is to achieved via the connection of capacitors, which produce a reactive energy, in opposition to the energy absorbed by this pump. It is an inductive load. The value of inductive load is 0.01 Henry, which is the pump capacity, absorbed a reactive energy of 50.93 kV reactive. Can be defined from this equation: a reactive power is equal to current squared times the inductive reactance. We learned previously that a pure inductive load, a current, lags the voltage by 90 degrees. You can see, on this graph, it is shown the instantaneous voltage and a current waveform. We enter the resistance value of a lights to 3 ohms, which is the total connected load of 25.44 kilowatts. This graphical presentation of a power triangle, which represent the relation between active power, a reactive power, and apparent power. Slightly increase the value of resistance for the lights to 3.2 ohms. As you notice, in the calculation data, the supply voltage is 400 volts. The result of inductive reactance of the pump is 3.14 ohms. The result of circuit impedance is 4.48 ohms. Take note from this value of a load current without the power factor correction is 89.19 ampere. This data is the result of apparent power without power factor correction is 35.67 kV-ampere. This data is the result of reactive power without power factor correction is 24.99 kV-ampere reactive. This is the result for real power of 25.46 kilowatts. The result of initial power factor is 0.71 lagging. This value is the improved power factor in the circuits. This is the equation. What is the amount of reactive compensation in the circuit? Let us perform the calculation, how it is achieved. The power factor improvement by adding capacitor from this circuit. Please observe the graphically waveform and the result of all data. We enter the value of capacitor to 45 microfarad. You notice the load current is reduced from 89 ampere to 85 ampere. The power factor slightly improved from 0.71 to 0.74. From this power triangle, did you observe, the previous apparent power is 35.67 kV-ampere. Now, the apparent power is reduced to 34.13 kV-ampere. As a result, by adding a capacitor, is to reduce the load on the electrical distribution system, thus increases energy efficiency. Again, increase to 90 microfarad. Our objective is to determine the required reactive power to be installed in order to improve the power factor, cosine theta, and reduce the apparent power. Increase to 135 microfarad. Observe how the power factor correction will achieve. Look at this power triangle. The shaded part, of light color brown, is the amount of reactive power has been corrected. Increase from 135 microfarad to 180 microfarad. Keep increase the value of reactive components of the capacitor. Look at the instantaneous sinusoidal power waveform. Below the horizontal axis is minus 3.44 kW. It means is returning to the power source. We need to achieve 100% delivered to the supply load. We saw in this presentation, the sinusoidal waveforms, that the phase angle, which is the current, lags behind the voltage by 28.25 degrees, nearing are in phase each other. Again, increase to 270 microfarad. Increase to 315 microfarad. Increase to 360 microfarad. Increase to 405 microfarad. Increase to 450 microfarad. Increase to 495 microfarad. To make it 100% power factor improvement, increase slightly to 497.35 microfarad. Now, you notice, from the sinusoidal voltage and current waveform, the result of angle is 0 degree. It means, we achieved a 100% power factor correction of 1. Look at the instantaneous power sine wave, is achieved the 100%, delivered to this load. No returning source of energy, or reduce the power losses, in the distribution system. As a result, it will increase the efficiency of the electrical system. Now, you understanding, if we add capacitors, it will reduce the reactive power component of an inductive AC system. From this result, the apparent and true power are equal. It means, is achieved 100% efficiency of the system. A higher power factor reduce the current flowing in the distribution network. The voltage drop in the conductor is also reduced, thus improving the voltage at the equipment. It will minimize also the power losses in the electrical system. The next graphical presentation of a power factor correction is more simple and more understanding with this electrical AC circuit diagram.